All right. So please, Pasha, start.
All right. Okay, so I'm really happy to give a talk here. It's like my alma mater department in Russia, so I feel a bit nervous because of that also. But also, actually, I hope that this talk will be maybe a little bit inspiring for the members of the department, because basically we study some questions that are interested for one community using techniques of another community, let's say. And the techniques of another community is basically techniques of the Department of Landau Institute. So as you see from the title, what I will talk about is so-called eigenstate optimization. And in particular of diagonal eigenstate optimization, this all I will try to explain. And I will try to introduce you kind of a solvable setup of this eigenstate optimization, the model where it's actually possible to study this phenomenon exactly, or at least to perform very efficient numerics. So this work that we actually started to do when I came to Ljubljana University, I started to do with my scientific gang. So who is my scientific gang? Is Rustam Sharipov, whom you probably also know because he was also a student in MIPT. He was giving a few seminars here. And our supervisor, Enei Ilievsky. So just a bit, this first few slides is actually my favorite because it's about people, and just a small reminder that actually science, it's about people. So how it started, I wanted to say. So when I came to Ljubljana, we had a discussion with Enei Ilievsky. Well, Enei Ilievsky is known actually for solving so-called quantum quench in spin chains. What is that? So this is all two questions of optimization. And actually in integrable spin chains, where you have a lot of control because of the beta ansatz, it's possible to show that indeed some initial states, they thermalize to generalized Gibbs ensemble, and it can be performed analytically. And mostly NA is known for that. And on this blackboard, so one evening we had a discussion where NA was trying to explain, and he was very excited that you see in spin chains, it's so powerful, we can do that. And then he was saying, and it would be really great to try to do something similar in some other setups, not in spin chains, but for example, in field theories, like in conformal field theories or in some integrable quantum field theories. And so then you see here, there's, I don't know what was this drawing, what I was saying, but there's some Remo models or something like that. There is some matrix elements and ATH already here. And basically from here, we started to, this was our goal, to see how it's possible actually to also study this kind of questions of optimization in the context of, well, in particular of conformal field theories, integrable structures of conformal field theories. I can't say we actually proceed a lot, but I think we did something, and I just wanted to tell you about this something. Yeah, but yeah. So okay, my plan will be more or less the following. I hope it will take only about 1 hour. I don't want actually to talk more, but let's see how it will go. So firstly, I will tell you what is this quantum optimization, what is actually the question, and what is the eigenstate optimization hypothesis, which is like a tool to basically explain this quantum optimization. And after that, I will need to talk a bit how it actually can be reformulated in integrable systems, and can we use integrable systems to study these kind of questions, because there we have a lot of mathematics and not only numerical techniques. And after that, I will second part will be mostly technical, where I will go to a particular model and a particular setup where we'll try to explain you how it's possible to study. All right. So what is eigenstate optimization hypothesis? So we actually interested in the question of optimization, which means the following. So we have some quantum system, and as I said, it's actually usually people think for a big reason, about spin chains. We have some spin chain, and it can be spin or half spin chain. and we initiate this spin chain in a particular quantum state psi0, and the spin chain has a Hamiltonian. And after this Hamiltonian, we have some evolution. And what we would like to see, that starting from some non-thermal state, we would like to see how we approach actually an equilibrium, how we approach a thermal state, but of course only on the local degrees of freedom, how it's happening. So for that, we actually, the goal is to explain this, but to explain this from the kind of first principles, because we actually know that as far as we work with quantum mechanics, it becomes just a linear algebra, because we just apply evolutionary operator to which is unitary to our initial state. And in some sense, if we think about the eigenbasis of our Hamiltonian, here it's like eigenvectors n, let's say, we can expand the dynamics in terms of these eigenvectors and eigenenergies. So everything is actually pretty explicit. And the thermalization, so one can think that, so this phenomenon of thermalization, often some observable of your interest, observable A, should be actually encoded in somehow in matrix elements of your dynamics, and how exactly it's encoded. This is the question. So one of the questions that you can ask is actually, well, thermalization firstly implies that you forget initial condition, you forget details about initial condition, and you equilibrate to, for example, thermal state, where the only thing that you know is a temperature. So the energy, the only information that remains is actually about energy, which is conservation law. If you have only one conservation law, which is energy, and the question is then, well, if you consider here a long time average of this local observable, this long time average can be expressed only through this diagonal ensemble where diagonal matrix elements involved. And you can ask a question. So this long time average value should coincide with the thermal value. But now actually this long time average value depends on Cn, which encodes my initial condition. But it should be thermal. So I should forget somehow this coefficient Cn. I should forget them. And the question is how actually the system can forget about its initial condition if they're actually here, they're present through this long time average.
Sorry, you consider homogeneous spin chains with some inhomogeneities?
Yes. The homogeneous.
Okay, thanks.
Yeah. And now the idea is actually the following, that when we consider a quantum quench, we don't do it in some sense from a crazy state, but we do it from kind of physically relevant states. And this is very important. So what is this physically relevant state? Well, when we start a quantum quench, we actually start with the state that has a well-defined energy density and suppressed energy fluctuation. So this we assume. For example, if we start from a ground state of some other Hamiltonian, not the Hamiltonian that gives us evolution, but of some other Hamiltonian, this state will have these properties of decaying correlations at long distances, which is actually equivalent to say that this state has a well-defined energy density, so the energy averaged is extensive with some factor, which defines your energy density, but also fluctuations actually sub-extensive. They can scale like L to the power of gamma, with gamma which is less than 1, which is important. And this is actually equivalent to say that your coefficients Cn squared, they are peaked at some particular value of energy. And so because of that, you can if you assume that the following holds, which is called diagonal eigenstate thermalization. So suppose you now consider these diagonal matrix elements, and they all look the same. They all just give you a value that depends only on the energy density, plus some finite size corrections. If you assume that, then in this long time average, these coefficients, they will be not important. You'll just sum them out to 1 because of normalization. And you will see that indeed the long time average will match with the value which depends only on the macroscopic details, only on the energy density. And so this is the idea of diagonal ETH, that actually diagonal elements, they know only about the macro state and not about some particular fluctuations of energy. All these details, they're encoded only in some corrections, finding some corrections. And this idea was formulated firstly by Deutsch and Srednitsky in early 90s, and maybe in a form of the ansatz for matrix elements. It was formulated in this paper by Srednitsky in 1999. And actually even more. So for now, yes, we kind of see that indeed, if we have this condition on the matrix diagonal matrix, for now it's only diagonal matrix elements, we can kind of explain the fact that we forget the initial condition and we thermalize to some macro state. But also Srednitsky proposed actually something even more. He proposed an ansatz for all diagonal elements. Because you can also be interested, like, okay, maybe long time average, actually I approach in long time average my thermal value, but what about fluctuations around this long time average? These fluctuations actually are small or no, because if you assume thermalization, you expect this thermalization, these fluctuations to be small. And so you also want to bound them somehow. And these fluctuations actually governed by off-diagonal elements, so they become important. And so the full ATH ansatz looks actually in the following. So diagonal, as I already formulated, states that yes, diagonal elements, here is only macroscopic information encodes. So diagonal element, if you sample states from the same macro state, you will see the dependence only on this macro state. And this already explains thermalization, while off-diagonal ETH tells you that actually off-diagonal elements are very small. They're suppressed. They're exponentially suppressed with the system size, and this suppression is with the entropy actually. Besides this suppression, which is like kind of at leading order, you also have some particular dependence on the omega. Where omega now is a separation in terms of energy. Well, and up to, of course, some kind of effective randomness, because there is a lot of these matrix elements, and so you can kind of study this statistically. And so there is also some kind of random piece, this coefficients R and Mn, that they can have some particular statistical properties, of course. But after averaging this out, after considering some particular energy windows, the only thing you will have is encoded in this F function. That basically tells you how matrix elements decays when you start to separate two energies far apart in terms of this omega. And the crucial thing here to bound, for example, temporal fluctuations, as I said, is just the suppression. Just the suppression. It's actually pretty enough to have this suppression that matrix elements, it turns out to be exponentially suppressed with the system size. But also this ansatz is actually used to study correlation functions. So if I want to study my 2-point function for example, in some temperature state, this ansatz actually people use a lot. Like nowadays, it's even it's used for higher point functions, but this also assumes some particular structure on this random coefficients Rmn. So yes, this is exactly what is the ATH about, some particular ansatz of the structure of matrix elements that holds in the thermodynamic limit. So this you of course you don't see this on a finite system size, on a finite chain, but you start to see this when you indeed go to thermodynamic limit. You start to consider the spin chain to be larger and larger, and you see that off-diagonal elements become more and more suppressed, while diagonal become kind of shrink and depends only on the macro state. Okay, so how it works, how people can check that. Well, there is, this hypothesis was formulated actually in 1999 as an ansatz for matrix elements, and it's still like seems to be state of the art of understanding of quantum thermalization. So even though it's like already 25 years. But the problem here is still a lot of problems, and the main problem is actually we are stuck in a sense that we can check that hypothesis only in restricted in a particular systems where we can do stuff. What is the systems? It's actually spin chains. Again, why we like spin chains? We like spin chains because the Gilbert space dimension is finite. And so if you have a Hamiltonian, we actually can consider this finite dimensional matrix. We can exactly diagonalize that using I don't know, just one command in Python. And we can have all information about eigenstates and eigenenergies, and we can study matrix elements just by this brute force approach. Of course, the issue is that, well, this ansatz is about the properties of matrix elements for large systems, but using this exact diagonalization, even nowadays, the system size that you can approach just around 20 spins, okay? So 20 spins 1/2. If it's spin not 1/2, but already like spin 1, it's even less. And another issue is, of course, there's actually no analytical control. So we do a lot of numerics. We compute a lot of stuff numerically. We publish a lot of papers. We're very kind of productive, but that's it. This is state of the art. How it looks like? It looks like that. Just some picture from a game view, very popular game view by Polkovnikov and his friends. Well, they take some model. It's in this particular case, it's not spin 1/2, but hardcore bosons, which is also almost spin 1/2, let's say. And they look at some two observables here, like some M and K. It's not even important what is this exactly. And they look how matrix elements, diagonal matrix elements, looks like when we write the energy. And what we can see here. So the left plot, when J prime, V prime equal to 0, corresponds for them to integrable case. And you can see the matrix elements, diagonal matrix elements are spread. And we increasing the system size, they not become kind of shrinking. So there is no well-defined function. So it's not, diagonal matrix element does not become a function of only the energy density, because close eigenstates can have very, very different values, eigenvalues, a very different matrix element, which is, of course, I mean, this is very natural, because to be close in energy in integrable system doesn't mean to be close, because you can be far away in terms of other charges. So actually, states that are close in energy can be from very different sectors in terms of other charges. And because of that, they can have diagonal element, which is actually very different. And so you don't see this shrinking. While let's consider something else, like when the break integrability, like in the middle or on the right plot, you start to see, things actually start to shrink with the system size, and it becomes like a well-defined function. Very good. So this is the usual check of the diagonal ATH that people perform. And in the case of fourth diagonal, how does it work? I think it's even worse. So in the case of fourth diagonal, let's start from the right plot, non-integrable. So people just plot all possible matrix elements for some observable, and as a function of the energy difference of the separation of the omega. And basically, so yeah, there is some spread, but you can this f function is basically defined like this kind of running average of these matrix elements. So it's like this red line here on the right plot, and you see for integrable case actually they're spread even more, and that's it. So actually this is how what is the difference in this kind of sense. The spread actually even more, even though these still matrix elements are still actually suppressed exponentially. Yeah. So now what I want to tell you next, let's see. Yeah. So yeah, again, this is the state of the art, 20 system size 20. This is our thermodynamic limit for now. And now the question is, can we actually go to integrable systems where we have a lot of control just from algebra, just from integrability structures? And can we study these questions there, even though, okay, there may be some differences comparing with chaotic system where there is a non-energy conservation, but well, we will maybe figure it out, or maybe we will see if there is indeed some, what is these differences? We will also, maybe we can also figure it out. But basically, the question is, can we use integrable systems as kind of to probe this kind of physics of optimization, because we have a lot of control? Well, for that, the short answer is yes. It's actually, I think it's good to try, and this is like ongoing actually work, more or less. But so let's go a little bit into that. But firstly, let me reformulate a bit the setup. So now in this setup, yeah, firstly, we need to answer the question, can we actually study these questions in integrable systems? Because, you know, okay, the chaotic systems, they do thermalize to a thermal state, but in integrable systems, there is a lot of conservation laws that prevent you from the thermalization. And the question is, well, then if there is no thermalization, what we should discuss? Of course, the situation is not like that, because even though there is a conservation laws, you should just expect that in the thermodynamic limit, when you again start the evolution from some particular state, you will go to a state that will know not only about the energy density, but also will know about the about densities of other charges that you have in your system. And so because of that, you should expect that you thermalize not to a Gibbs state, but you thermalize to so-called generalized Gibbs state, which is basically, well, basically similar to a Gibbs state. You just give a chemical potential to each charge, and you construct this beast, the density matrix. Now, actually, it's a complicated object, yeah, but this is what you in principle should expect, that you will thermalize to this generalized Gibbs ensemble. And it's indeed what happens, and this is what I was started, right? So this from the studies of Enielewski, who kind of proved that in spin chains this indeed happens. We see the appearance of generalized Gibbs ensemble. So yeah, in principle, we can again ask the question: can we explain the now kind of equilibration to this generalized Gibbs ensemble? And yeah, we can then use the same logic, the same arguments. Then maybe now we just need to have in mind that the macrostate, the definition of the macrostate has been changed. Before, macrostate was defined just using the energy density, while now we need to talk not only about energy density, but also about the densities of higher charges. So having this in mind, we can say, so maybe diagonal ETH now we should formulate in the following way: that matrix elements now, if we sample them from the same macrostate, and macrostate is defined by densities of my charges, diagonal elements should start to depend only on the information of the macrostates plus corrections. This is like a natural extension. Well, and indeed, this is what happens. So you see on the previous plot, I was showing you, in integrable system, if you take eigenstates at a closing energy, they were very separated matrix elements, diagonal matrix elements. But yeah, because of other charges. So now if you take kind of other charges into the consideration, everything becomes fine. And indeed, this has been checked that this actually happens. The diagonal matrix elements depends only on the macrostate information. So like in particular, the works of Anatoly Demarsky, there is a lot of them that devoted to that. He's maybe not here, but okay. And a little bit more complicated for now, currently, for current understanding, let's say, is about off-diagonal ETH. Because now here, there is some studies of off-diagonal elements in integrable systems that actually utilize beta ansatz, and because of that can really perform numerics, let's say, for much larger system size. And according to these studies, well, they claim that actually the form of matrix elements is slightly different from what was expected from ATH. What is different? Well, firstly, both there are two papers. They're pretty recent. So another one is a Hive, but maybe now it's already published. They're pretty recent. One of them by Fabian Essler in the Lieb-Liniger model, and another from Vincenzo Alba in XXX chain. The conclusion is more or less the same in terms of the structure of matrix elements. So the claim is that matrix elements integrable model, for instance, they studied the thermal ensemble. In thermal ensemble, they suppressed not exponentially with the system size, but there is even bigger suppression, parametrically bigger. There is extra log. So the suppression, the leading term is L log L, instead of just exponential with the entropy as it was in the ATH ansatz. And also this effective randomness actually comes already at this order. So like in the ATH, there would be L to the power of 0 near to this randomness, MMN. But now it's already here, it's already at the same order, at the order of L. So the randomness, it's actually the width of this randomness, it's already at leading order as well, which is a bit surprising, which is a bit different from the ATH, from what we expect from chaotic systems. So this as well, this kind of papers also maybe motivated us, let's say, because the question, of course, now, like, is it indeed like, so maybe integrable systems, they're different in terms of the structure of diagonal matrix elements. So on diagonal side, I think now it's kind of consensus, pretty the same. So diagonal matrix elements, they know only about macrostate in both chaotic and integrable systems. Well, as far as there is no any kind of tricks that happening. But about off-diagonal matrix elements, how they look like in the thermodynamic limit, it's a little bit open problem, let's say, that I will try to tell you about what is our understanding of that problem. Okay. So okay, this may, let's say, part 1 finished. If there are some questions, please let me know.
Sorry, at last, at this transparency, you have no any randomness. It's just conventional XXX spin chain, yeah?
About what exactly?
I mean, the last formula at this slide, you mentioned it's just the conventional XXX without additional randomness.
Yes. It's just XXX.
Okay, thanks.
Yeah. Okay. So basically, this will be the main concern of this talk. How off-diagonal elements looks like in the thermodynamic limit. Well, in integrable system and chaotic, it actually doesn't matter for me, because from my perspective, it's kind of the same as far as you take care of charges. So firstly, let me reformulate a bit what will be the quantities of interest that we would like to study, we would like to define and to compute in some particular model. And after I will define them, we will go to details into some exact well-defined model, and we will try to see what is what. All right. So firstly, what we want to see, actually, we want to go a little bit beyond the standard of diagonal ATH. So what does it mean? What does it mean? It means the following. So usually when people discuss ATH, they think about off-diagonal element between two eigenstates that are separated in a finite amount of energy. While now we actually would like to study all possible separations. We want to say, okay, but what if actually energy separation is not finite, but scales somehow with the system size, like L to the power gamma? Why it can be important? Well, at least it is important, of course, as far as gamma equal to 1. What is gamma equal to 1? Gamma equal to 1 means that energy is separated already in an extensive amount, so you proper matrix element between different macrostates. What does it mean to proper matrix element between different macrostates? Another thing, so maybe I didn't emphasize, but I'm actually interested in local observables, and locality is very important, even though people do not understand very well why it's super important. So at least on mathematical side, intuitively, it's very clear. We are interested in local operators, and we act on eigenstates with a local operator. Of course, it's not like some very highly non-local operators like projectors, for which, of course, nothing like that will happen, but it's a local observables. And now if I think about my eigenstates that correspond to one macrostate, and I act with a local observable, of course, this local observable will never change the structure of this macrostate. It will be still the same macrostate. So in some sense, you expect that there are any overlaps between different macrostates. Or, in other words, the suppression is actually, you expect suppression to be much, much bigger, because this matrix elements characterize you, but what is the probability of the transition after you act with this observable? So for gamma equal 1, where this is a two different macrostates, you already expect, but the suppression actually should be much bigger than the exponential, because you should see the difference. Indeed, the local observable should map only matrix only eigenstates that are close enough in energy. But if you expect the difference for gamma equal 1, what then happens when you start to decrease gamma to gamma equals 0, where indeed you probe finite energy separation? So we would like to actually address this kind of question. So in some sense, you kind of expect ATH kind of scaling of matrix elements. There should be some breakdown. It cannot be that it's always exponential suppression. There should be some breakdown. And how this breakdown looks like, this is what we would like to actually see. Just let's say for now, just because of like curiosity, let's say, okay, just how this locality looks like, why this local observable cannot map it, and what is how to mathematically see that it's indeed cannot map. So what is the suppression, how it looks like. And so what is another thing? Another thing I want to say, yes. So secondly already, we will work with the actually integrable model. And so because of that, we need to be very careful. So integrable model is actually a lot of responsibilities because there's a lot of charges. In chaotic model, it was just a Hamiltonian. You need to take care only about the energy separation. Now we need to take care about separation in all charges. So you need to define a proper distance between your eigenstates. Okay. So let's define this proper distance. All right. So as I said, chaotic system, just energy, macrostate defined just by energy density, and the distance between eigenstates is just the energy separation. But if you do integrable and you have macrostates that are defined by densities of all charges, well, the distance between different states should be also defined as kind of the average difference between these charges in these eigenstates. So you should take this into account. And this is extremely important. And now I should say, this is actually very hard to implement numerically, because when you have numerically a Hamiltonian, that's it. This is your matrix. You know energy, okay, because you generalize this matrix. Do you know other charges? Do you know? Do you label all charges with all eigenstates with all charges? No, you don't. It's actually a complicated problem. It's not very easy. But one of the kind of claim that our understanding is that this is indeed important. This turns out that it's important for the structure of matrix elements, as we will see, I hope. All right. So yes, we will take care about this distance. We will look, okay, how these guys are separated in terms of all other charges. We will not take care only about the energy, because the studies before, that was I said, the studies in integrable systems, well, actually, they were focused only on the energy separation, and there is some consequences as we will see actually. So the results they see, the strange result, strange suppression, bigger than in ATH, strange randomness, kind of in another order. All this comes actually from this fact that you just don't take into account another charges. You don't know how other charges fluctuate between your eigenstates. Okay. Very good. And now, so after we have this distance, I want to say, now we want to study matrix elements actually in some ensembles of states. So we want to, of course, we will do this somehow. We will work with with systems that has a lot of number of states, because it's thermodynamic limit. So we need to somehow sample states. We will sample that, of course, from some ensembles, from particular ensembles. And now we want to say these ensembles should have well-defined fluctuation. So, well, firstly, we assume that some ensembles of states correspond to some particular macrostate, to some particular densities of charges. And we will say that this ensemble of states has a fluctuation scale gamma if just charges basically fluctuate on this scale. For example, if you have a Gibbs ensemble, a well-known fact, in Gibbs ensemble, the energy fluctuates as L1/2. In the generalized Gibbs ensemble, all charges fluctuate as L1/2. So Gibbs ensemble is an example of an ensemble with fluctuations gamma equal 1/2. So we actually don't want to take Gibbs ensemble, because Gibbs ensemble has a very well-defined fluctuation, and we would like to probe this dependence on this fluctuation. So we would like to define an ensemble where we can actually change this fluctuation. This is crucial. This is very important. So an example of such ensemble can be for instance, microcanonical. If you have a chaotic system where you have only energy, you need to define a microcanonical ensemble where you have a shell. So microcanonical ensemble defined by some shell D, where you collect all states in a given shell. And you just need to scale now this shell with the system size, like L to the gamma. So this will correspond to what we want, the particular fluctuation scale. Or in integrable, which will be, of course, much more complicated problem, you now need to kind of generalize this microcanonical ensemble. And so you need to collect only states that in all charges fluctuate like that, in all charges. Yeah, numerically, very tricky, but okay. We will actually, in the system we will discuss, we will do it somehow because of some nice properties. And yeah, there is again the note that maybe I already mentioned, that it's, conceptually it seems even very wrong to actually deal with integrable systems, to do numerics in integrable systems and study them in microcanonical ensemble. And this is what we do. But this is state of the art. Okay. And let's see what is the consequence. All right. As I said, okay, now we have this ensemble. So let's say we define. You can have in mind these generalized microcanonical ensembles where we control the scale. Now what we want to take our observable of interest, where we can compute something. Of course, it's not our choice actually. It's something we can approach. And we are interested in the properties. Well, now I will take the logarithm from this guy, because I expect this guy to be suppressed exponentially. So I will take a logarithm just to work with something of order of 1. So I will work with this kappa Mn. It will be everywhere, this kappa. So just remember, kappa is basically logarithm of matrix element. Well, divided by L because you expect that. You expect this will be to be of order 1. It's actually not, but you expect that from ATH, let's say. So we define that instead of just a matrix element. And when now you sample states, another state, another state, and you compute matrix element. These matrix elements, so they will form some distributions. This kappa Mn, you can think about them like a pseudo-random numbers, correct? And so you can characterize what the properties these pseudo-random numbers have. For instance, you can define a suppression rate, which is just the average of kappa Mn. Or you can define what is the effective distribution width of these guys, or what is the distribution itself, what is the PDF of the distribution. So this is the things we are interested in, right? So there is a lot of matrix elements, but we kind of saying, okay, let us just think about statistical properties for now, all right? So we just want to kind of simplify that, the picture, and as well, we actually will be interested, what is the order, how this suppression rate scales with the system size, how the distribution width scales with the system size. So we're interested in the scaling exponents P and Q that in principle can depend on gamma. And this is what we want to address and want to study. Is it actually, if they actually depend on gamma or not? For instance, if we take ATH prediction, ATH predicts that matrix elements suppressed exponentially with the system size. So P is just 0. Using this, my definition, while the randomness comes at next order, so Q is just -1. The width, it's only at next order, the randomness. And if we think about this result of, okay, it's very bad to why I wrote Essler, but one of the paper was by Essler, so it makes sense. If you think about these results about Lieblinige or XXX chain, what they obtain, P was equal to 0 as well, up to this log correction that you don't feel on the definition of this P. But Q was also equals 0. The randomness was the same order. It was the same order in the system size. Okay. So yeah, this will be the main quantities of my kind of interest. And maybe now also kind of formulating this setup. Maybe I will ask again if there is some questions. Yes, and yeah, okay. О, Алексей, вы в поезде?
Да, в поезде. Ну ничего страшного, я слушаю, все отлично.
Okay. Okay, I can proceed, right? It's pretty. I mean, there is no rocket science. Just okay, these matrix elements, we want to know how they kind of suppressed, or what is this effective randomness, depending on this fluctuation scale in the ensemble. That's it. The question, more tricky question, can we actually do that? It's really good to define that, but can we actually do that? For that, it's kind of seems to be a complicated problem, because we need to somehow know matrix elements. So we need some model where we can do that. So what we need to do? We need to have a model where we have, firstly, access to the matrix elements, which is super rare. Even like if you have an integrable system, beta ansatz, okay, very good. We have beta ansatz. Can we solve beta ansatz? No. Can we know matrix elements using beta roots? No. So actually, well, in some cases, yes, but these expressions, like to work with them is actually very complicated. So even in beta ansatz, even just to take some beta ansatz in segment model, it's not enough. It just doesn't give much. It's very complicated, even in this sense. It's not that okay, integrability is nice, a lot of mathematics, and everything is good, everything is easy. No, everything is actually complicated. So firstly, yes, there should be some access to matrix elements. Secondly, in this model, we should be able to define an ensemble like we want. We would like to work with ensemble with different fluctuation scales. So it's not just a thermal ensemble that we sample from Gibbs and that's it. I mean, it's not like that. So, but yeah, the next thing I want to tell that actually there is a model. You can do something. There is a model. So the model is well-known model for, I hope, well-known model for the audience here, for Alexey Viktorovich. It's basically well-known for sure. It's a quantum Benjamin-Ono. Okay, I'm talking for 45 minutes. It's crazy. Okay, maybe it will not take 1 hour. Sorry, 1 hour and 15 minutes. I promise. So,
the default time is 1 hour and 30 minutes.
Yeah, I think it's a torture. I think it's too much. But now I feel that maybe I will have to torture you, but it's okay. I mean, for me, but yeah. So okay. The Benjamin-Ono. I will explain. I will give more details, but now I just want to emphasize, like, shortly, a sketchy. Quantum Benjamin-Ono. Why it's nice? So quantum Benjamin-Ono is particular integrable structure in conformal field theories. First of all, first fact. Fact number 2. It's very nice systems because everything can be described using Young diagrams. You know eigenvectors, you know eigenvalues, you know matrix elements, and everything encoded in combinatorics of Young diagrams. Good. One issue. Actually, you need to take thermodynamic limit. So actually, you need to really take this Young diagrams very big. So you need actually to play with these combinatorics, but like on a large scale. And so here, kind of the complexity still comes, right? So everything kind of known on the macroscopic level, but you need to push that to the thermodynamic limit where the system size is so huge and all these Young diagrams become so huge, and you need to work out this thermodynamic limit. So this is still the problem that we will try to overcome. But still, yeah. So at least we can still obtain some analytical results, which is actually rare. It's very rare for these kind of questions, and as well as pretty good numerical result. It's not spins 20. It's really much better system sizes that we can probe. It's incredible, actually. So yeah. So let's go to that. This is actually first part. So when I just kind of saying, okay, we studied that, it's maybe interesting, maybe not, and we studied in this model. Now I will go to particular details. I will define this model, and I will try to explain how we proceed with all this study. All right.
Sorry, by the way, Benjamin-Ono is just like a limit of Calogera.
Exactly, yes.
Is it possible to perform all the stuff for Calogera case?
Yeah, very good. So let me comment on one particular spot. Or if I will not comment, I kindly ask you. So on the moment where I will claim that matrix elements are null, I should comment on Calogera. Yes.
Okay.
But this actually will be the main subtlety. But okay, yeah. But indeed. Okay, so let's go into details now. Now let's dive into that. So Benjamin-Ono. So I will consider so-called Benjamin-Ono 1 simplest setup. this hierarchy constructed just using one single bosonic field. I will not consider here P and Q modes, so not zero. There is no zero mode. There is no Q operator. There is only creation and annihilation operators, AN. And I will need the U1 current because actually stuff is defined using this U1 current. So charges can be defined using this U1 current. How they look like? They look like that. So they are kind of local. So they can be defined as integrals of local densities, kind of local densities. Why? For instance, the first density is nothing but well, the kind of Hamiltonian density for the free boson, but this one does not specify actually the hierarchy. You need to do some. You need to specify next charge, and this next charge will specify the hierarchy. Next charge looks like Q2, and it's like J cube, and there is another term that also involves the Gilbert transform. The Gilbert transform. And what I wanted to say, yeah, and you can, for instance, you can write this how it looks like in modes, how these charges looks like in modes. So the first one, very simple, is just if you have a state which is a Young diagram, just counts as usual the number of boxes. The second one is a little bit more complicated, but you see in modes, it's actually this Gilbert transform looks still very simple when you go to Fourier, so it looks pretty nice. So yes, as Alexander Sergeyevich mentioned, this system actually, well, it was discussed in this paper by Awata et al. as a field theory of Calogero. So this appears as a field theory of Calogero, first thing. Second thing, you can think about this indeed as a quantization of Benjaminona, of a classical Benjaminona. For that, you need to take some proper limit, beta goes to infinity or beta goes to 0, and yes, to be you will find classical Benjaminona. All right, why this one is nice for the problem we want to study? Well, this one is nice because it's very cute. So look, firstly, eigenstates. It's like in Calogero. Well, in Calogero, eigenstates is basically orthogonal polynomials. Here as well, we need Jack polynomials or symmetric functions. So to each Jack symmetric functions that are labeled by partitions, we can associate an eigenstate. I'll not tell you how, but it's pretty simple, like more or less. I will not need that. What I will need maybe is the fact that also eigenvalues can be pretty easily computed. The eigenvalues, the sum of them, the eigenvalues on the particular eigenstate lambda that is defined by the Jack polynomial is given by this sum of kind of beta roots in some power, this U cell. So to each cell, you associate a beta root. And these beta roots, they in some sense, you don't need to solve beta equations. Beta equations are solved just by symmetry in this case. Beta roots are pretty simple. Beta roots, in this case, it's so-called a content of a cell. So let me just use as an example. So what you do, you have your Young diagram. To each cell, you start to associate a beta root. For instance, to this blue cell, what you need to have, you need to have a coordinate, a horizontal one, a vertical one, and using this formula, you just evaluate the beta root. And after that, using all these beta roots, you basically go to expression for the charge, and you compute all values of all charges. Okay, so system with beta answers basically solved by symmetry. Well, in this case, it's Youngian symmetry. All right, and this one, I think, system with no spectrum, good. Another, what we need, a matrix element. And the question, are there some observables where matrix for which the matrix elements can be evaluated? Yes, these observables are modified vertex operators. So you define the what you take your bosonic field and you take a part that involves only creation operators and the part that involves only annihilation operators. And using this, you define the modified vertex operator. So here is this, there is extra alpha 0. So if alpha 0 would be 0, exactly 0, it would be just a conventional normal ordered vertex operator. But now it's a bit modified. So these exponents close to 5 minus and 5 plus, they are slightly different. And this is indeed actually necessary for the matrix elements to be expressed in a very a nice way. Because now you see the shift alpha 0 actually depends on beta. So for different beta, there is a different modified vertex operators for which you know matrix elements. And how this matrix elements looks like? Well, they described also by combinatorics of your diagram. So if you take a state that corresponds to some diagram, what you need to know about this diagram is legs and arms of cells. What is legs and arms? Very easy. So if you have a blue cell here, the arm actually is just this distance here, and the leg here is this one. Well, it's called leg and arm because usually, like, there is another convention for diagrams. It's usually inverted, so it's indeed looks like a human with a leg and an arm. But in this convention, of course, this leg is not actually a leg. It's going up. And also you need to say what is, so if I take a cell outside of the diagram, I also need to know what is leg and what is arm. And this is just kind of linearly extended. So if I have a cell here, so this is this distance, leg, but just with a minus sign. If I have arm of this cell with respect to this diagram, it will be this distance, also with minus sign. So I actually need to know how to compute legs and arms, not only of cells inside the diagram, but of cells that are not belong to this diagram, to compute matrix elements. How to compute matrix elements using these legs and arms? In the following way, taking, for instance, diagonal matrix elements. So you now can take these Jack polynomials and you can start to compute these matrix elements explicitly using these vertex operators. And you can see that these matrix elements actually will be polynomials in alpha. But if you just take vertex operator, this polynomial will be whatever. There will be no structure. But the statement here, this polynomial actually has a very nice factorized form. So actually, you know where zeros of these polynomials are, So you see, it can be represented as just as a product over all possible cells of your diagram. And there are some factors that basically includes the functions that use arms or legs. So this is basically what you now need to take into account. Just very nice factorized form. If you just take another basis, not a Jack polynomial, but something else, just a usual basis of a free boson, this polynomial matrix, it will be also polynomial in alpha matrix elements, but the zeros will not have this beautiful structure. So yeah, there is some magic happening on this side. And the off-diagonal element as well has a factorized form. Now it includes a product over cells in lambda in one state that correspond to Young diagram lambda, and another that correspond to Young diagram mu. And there is again some functions. There is actually, and it's not independent on lambda. So there is some kind of interaction between them, because, for example, here is a product over cells in lambda, but this function f1 lambda mu, to compute that, you need to compute an arm of this cell, but with respect to mu. So in this sense, there is the interaction between two states in these matrix elements. It's not like independent from one to another, these products, but there is some interaction between lambda and mu. But here again, you see factorized form pretty explicit. Now here I cite a paper of Alexey Viktorovich, which is basically was devoted to similar matrix element, but not in this Benjamin-Ono, but in Benjamin-Ono 2, where conformal field theory is mapped to a free boson. And here you can also define some hierarchy, which is called Benjamin-Ono 2, that basically correspond to classical Benjamin-Ono 2, where there is two fields, not one. Now this formula is actually for this main case, Benjamin-Ono 1. But yeah, it can be generalized for any hierarchy. Okay. So far so good or no?
Good.
Yeah, it's fine. Mm-hmm.
Okay, good. It's fine. Let's see. So yeah, now you see, system where basically, again, at least on a microscopic level, if I take small diagrams, all these matrix elements, I can compute them just by hands, and I can see that they indeed have this factorized form. But now again, I will need to consider thermodynamic limit, and let's see what happens. What actually I should do with these kind of formulas. Yeah, so let's try to understand what is hidden in these matrix elements. Yeah, just a remark. I will actually fix beta equal 1 here. It corresponds just to case of not Jack, but of Schur polynomials. There's three reasons. One reason, charges becomes just local. There is no Gilbert transform. It's a bit nice. Yeah, just a physical motivation, nothing. Okay, it's not actually important. It becomes very local. Second reason, the vertex operator becomes just now a really usual vertex operator. It's not modified one. And this is also, for me, it's very nice. It's like more, indeed, physically, for me, it's more interesting. Because this is a primary field. Now this guy is a primary field of my, like, for example, free boson CFT. And the third reason, well, actually, you see matrix elements, it depends on beta, but in a pretty regular way. And the things that I will tell you, it can be generalized to arbitrary beta. So if you let me, can I just put beta for one? So my matrix elements will look just like, well, not mine, matrix elements for Alexei Viktorovich will look just like that. Take diagram, compute arms and cell and legs, and here you are, right? So it seems very simple. So let's see. Okay, maybe 15, maybe I can actually do that in 15 minutes. Let's see. All right, let's now go to thermodynamic limit. What is thermodynamic limit now? So let's define macro state. So now, firstly, if I take a diagram, about diagram I think as a state, and now if I take a diagram, this diagram I can characterize by just this discrete shape, which is this red curve here. It's just a discrete shape as a function of x. And this discrete shape encodes me diagram completely, and I will think about this discrete shape. Why? I will tell you in a second. And now this distance that I was talking about between different states that you need to define using all charges. Now you can just define that actually using diagrams, because you know that all charges, all eigenvalues of charges encoded in these diagrams. So you know that now your language is actually not about charges, but your language is about these Young diagrams. It's like in beta ansatz. Okay, you can think about charges, but actually the proper variables are beta roots. It's better to think about beta roots, about their distributions. This is your degrees of freedom. And charges, okay, and also you can compute charges if you really need so. And here it's the same. It's actually the main kind of object is this shape function and not the values of charges. Okay, and now. Okay, let's go to the thermodynamic limit. So thermodynamic limit, in the thermodynamic limit, I would like to define it like that. It is such states that have an extensive energy and all other density of all other charges. So all values of my charges are extensive. And of course, because I know how the charges are expressed using these beta roots, this implies some constraints on my beta roots. So because now I know that all these sums of these beta roots should be scaled somehow with the system size. And so now I see that this is actually equivalent to the fact that my Young diagrams that I should consider, number of cells in these diagrams should grow like L squared. So if I consider system size L, my macro state is defined by Young diagrams with L squared cells, very big number of cells. And what is happening in this limit, that you start to have very huge diagrams, and if there is if you define some particular ensemble, like for example a Gibbs ensemble, what will happen that all of them actually will be almost look the same in terms of the leading order, let's say. So you can define this rescaled shape function. You know that in both directions you're going like L. Your Young diagram in both directions is like L. So you define this rescaled shape function. And now this shape function, what can happen? That this shape function can be, for some particular ensemble, can go to a well-defined function that is called the limit shape. So your macro state is actually now defined by this limit shape in the ensemble. And of course, in this ensemble, there will be also some fluctuations. So it will be a limit shape and some fluctuations around. And this limit shape is exactly your macro state. So now for instance, your densities of all charges, you can evaluate using this limit shape function, just as some simple integral. And that's it. This is your macro state, actually. The limit shape. And the fluctuations in the ensemble are encoded in the next order. And we will take care about them as well. But okay, so now you see, again, the language now. Before I was talking, macro state is defined about in terms of densities. Now I don't need densities. All densities are encoded in this one function, psi x, which is a limit shape. Okay, and now also you can compute the entropy. So of this limit shape, you can compute the entropy, which is just a combinatorial computation. So you kind of compute how many microstates realize this limit shape and you can evaluate the entropy. There is a particular expression, so this can be done. It's not a big deal. And with this entropy, for instance, you can consider kind of analog of TBA equation. So you can ask a question, now if I consider a generalized Gibbs ensemble that corresponds to this partition function, now this partition function I can rewrite like a functional integral over all possible limit shapes. And this functional integral has some free energy, and in this free energy we put the entropy that kind of count how many states correspond to this particular limit shape. And just minimizing this free energy, you can find a limit shape that corresponds to your generalized Gibbs ensemble. So this kind of the analog of TBA equations, let's say, that you can also here derive pretty easily. So yeah, and here there is one example which is actually important for me in terms of these Gibbs ensembles. One limit shape that is important for me. This is the simplest Gibbs ensemble you can imagine. What will happen if you just consider the only one chemical potential to be mu and all other to be 0. So it's actually, what is this? It's just a Gibbs state in terms of your Young diagrams, that Young diagrams weighted only by the number of cells in these diagrams. This ensemble was considered maybe firstly by Vershik, and you can compute, for example, you can solve these TBA equations. You can find that the solution is a particular curve, which looks like here on this slide, and this curve is known as a Vershik curve. So this curve that corresponds to this ensemble. And basically, what we will do, we will sample from this ensemble. We will sample states from this ensemble, and we'll try to see how matrix elements from states from this ensemble looks like. But for that, we actually need to know fluctuations. Before going to this, fluctuations in this ensemble, in this particular ensemble of diagrams, I will tell you shortly about one particular states that you can consider just to gain some intuition about matrix elements. What is this state? These states are very simple. These states are triangle diagrams. So now forget about Vershik. Now we're just working with matrix elements, and we're working with very huge Young diagrams, and we're asking how matrix elements looks like. So for that, we can just take some diagrams for which legs and arms of the cells can be evaluated pretty straightforwardly and very efficiently, such that you can even perform some analytical computation using a particular form of the matrix element. And of course, such states it's diagrams like that. It's just a triangle diagram, or how we call it, maybe ladder diagram. Yeah, triangle diagrams. So now you can just take one diagram that has L cells here, L cells on another side, which is blue one, and the diagram which is separated a bit. So it has L plus D cells, and this D is exactly this kind of distance between these two. Now, pushing this D bigger and bigger, you would like to see how the matrix elements changes. So you can already consider now how the suppression increases when you start to increase D, right? Or you can scale D somehow. You can scale D with the system size, and you would like to see how the matrix elements changes. So in this case, indeed, this calculation, these states are nice. You can perform calculation analytically, and what you can see that actually in the particular regime where this D is large and as well L is also large, and D is still much smaller than L, you can find some particular form from which you can extract some information. Well, which kind of information? Well, when you start to scale D like L to the power of gamma, you see that there is 3 regimes. So in this expression in the middle of the slide, there is like 2 terms. One is like a constant term and another is like a correction. And in some particular regimes, this correction starts to be leading, but for another regimes, it's not leading, it's only subleading. And this happens for different gamma. It depends on the gamma, actually. For instance, when gamma is less than 1/2, you see that the second correction in the formula in the middle of the slide is actually going to just 0. And so you have only constant term. And so the matrix elements is indeed exponentially suppressed. But now taking gamma bigger or equal than 1/2, you see that, now second terms start to be leading. And so the suppression actually of matrix elements becomes bigger. You will have even more. First of all, you will have not only exponential, but like L to some bigger power, in this case, L to the power 2 gamma. And there will be also some particular log correction. So remember, there is some log correction from previous papers I was discussing. Okay, there is some recent papers in XXX chain, in Lieblinge, and there is some suppression with log correction. Here you also see some log correction. Okay, and another case is a case of different macrostates. When you take gamma equal 1, that corresponds to the case of different macrostates, you see the log correction just disappears actually. And you see that matrix elements is indeed suppressed, but even more, it's suppressed like L squared, right? And also you see all this kind of nature of this suppression. When you write gamma, it's not like it's always exponentially suppressed, but there is something happening. In particular, in this particular case, at gamma 1/2, where the suppression becomes parametrically larger than just exponential with the system size. So in this particular case, you can kind of figure it out, and it helped for us because it really gained some intuition how maybe it should work also in some more physical ensemble, like for example the Vershik ensemble. Okay. All right. Are there some questions on this point? Because I feel a bit lonely. Okay, if no, I will.
There will be comments after your talk, but let me postpone it.
Okay. Yeah. Okay. So now, the summary of these slides. Yes. Firstly, you can just take some simple states from which you can extract something analytically. And now let's use this kind of analytical intuition to go back to the Vershik ensemble. So now again, let's consider some ensemble from which we will sample. And we will take just an ensemble, the simple ensemble that corresponds only, where we weight Young diagrams only using the number of cells. As I said, okay, there is a known limit shape, which is called Vershik curve. But what is also nice about this ensemble, that besides the limit shape, the fluctuation is known. Well, first of all, this fluctuation is of order of L1/2, as it is in the thermal ensembles. This is not a surprise. But what is also known, the particular form of this fluctuation. So the fluctuations actually here represented as a Gaussian noise, and the covariance matrix of this Gaussian noise is exactly known. It's expressed also like, so here's this covariance matrix that is written. It's expressed using this derivative of the Vershik curve, basically. But now, so what is the trick then? So if we know, you can sample then states using this knowledge, because you don't need to sample fairly from the Gibbs state, but you can just use this formula, kind of approximate formula, because now you know you need to take the perfect Vershik, the state that corresponds to the perfect Vershik curve, the limit shape, and you need to put some noise, the Gaussian noise, and this Gaussian noise you can generate on your computer. So this is actually, it's very efficient to do this numerically. It's much more, you can do that on much bigger system size than just fairly sample from a Gibbs state, for example, using Metropolis algorithm, something like that. This one thing, but the second thing, but then you can also just change the magnitude of your noise, the magnitude of your fluctuation, and define the ensembles that we wanted to define, these ensembles with another scale of fluctuations. So you can just say, okay, maybe there is no L1/2, but there is some D, and this D scales like L to the gamma. And this will be exactly, now again, from this you can again sample, there is a perfect Vershik curve, and you put some noise, you just change the amplitude of this noise, but this noise is always the same. And this is the way how we can probe these different ensembles with different fluctuation scales. So there is the same fluctuations, but different scale. All right. So, and this is nice because from this we can do efficient numerics. This we can indeed just sample these states. You can compute matrix elements. It's matrix elements represented as a product in a product form, so you can perform it very efficiently. And so the results are the following, actually. So now I come back. So there is this suppression rate that I was interested. You sample matrix elements, you collect this effective random, pseudo-random variable, kappa, which is a logarithm of matrix elements. And this kappa has a suppression kind of mean value and the distribution weights. And now we just look at this suppression and the distribution weights, how they depends with when we write D. And we actually see that this suppression rate and the distribution weights, they becomes a good functions of some particular variables. In this case, it's this variable U, this variable here, which is cook-up from D and L. It's actually the same variable that was on the slide, with the line. It was here. It was this guy. So that's why we knew actually that we should search something for that. And in this particular case, it worked also. So if you just plot as a function of this U, you see that for larger and larger system size, you see a collapse. And the suppression rate becomes a function of only of this U. Moreover, the asymptotics here, it's linear. So it's a linear asymptotics. So kappa average becomes just proportional to U. And for distribution weights, almost the same happens, even though the scaling variable is a bit different. It does not contain this log. There is no log anymore, but it just contains this squared divided by L. And again, you see it becomes for bigger and bigger system size, it becomes good collapse. And D kappa is actually just proportional to E, So we see these collapses. And just from this information, knowing that indeed the suppression rate depends only on this U and the distribution weights on this V, and now taking D again to scale somehow with the system size, you can actually extract the information about P gamma and Q gamma, about what will happen if you consider fluctuation scale to be for the gamma. What will be the rate of suppression? What will be the rate of the randomness? And so the result is from that is the following. So again, now there is this mean guy who is the kappa mean, so the characterizing you how small the matrix elements. So I just reminded kappa. I'm working with this guy. I'm working with this guy with the log of the matrix element. So kappa characterizes how small this guy, and D kappa characterizes what is the effective randomness. What is the width of this effective randomness? And now I'm just asking how they scale with the system size. So I'm interested in this P and Q. And now you see the following structure. What I want to tell you here. Okay, so this, okay. Well, for gamma equals 0, actually everything starts like that. P is just equals 0. And Q is just equal to -1. And this is exactly like in ATH. Like in ATH, it looks like that. There is a suppression rate. There is suppression like that. There is F function, and there is a randomness. This randomness only at next order from the suppression. This separation is exactly happening here. It's indeed like in ATH. But as far as you start to increase gamma, well, the suppression of matrix elements is still the same. Suppression is still exponential. But the effective randomness is actually starts to decreasing in the order. So this effective randomness become bigger and bigger and bigger and bigger until there is becoming they coincide with gamma 1/2. Actually, it's good. It's better idea to draw it blue. Sorry. And at gamma 1/2, you see suppression. Even suppression becomes bigger, and they always go just at the same order. Also, there is a log correction, which is a bit important, and the log correction that we can extract, the log correction in the suppression rate. And so it actually matches with gamma equals 0 with this kind of ATH assumption about the matrix elements, as well as it matches with the gamma 1/2. When you fix gamma 1/2, it matches with the known results about integrable systems. Well, why it matches for gamma 1/2? It matches for gamma 1/2 for the following reason. the studies in integrable systems, they use microcanonical ensembles. They don't control fluctuations of other charges. And because they don't control that, other charges fluctuate, and of course fluctuate on the scale L1/2, like in a thermal ensemble. And so effectively, this study is about 1/2, even though they don't know that. And we, in our setup, we match at gamma 1/2, we match exactly with what they have. We match with the log correction, we match with the distribution of matrix elements, with the width, how big is the width of matrix elements, and so on and so forth. So yeah, that's it. This is the hidden structure in these matrix elements in the thermodynamic limit. Let's put it this way. And maybe, okay, almost. Maybe on this I can summarize a bit, and that's it. I can just finish. So what I told you that, yeah, first kind of lesson. It's more like a lesson for us, but I think for numerical people, it's a big lesson, but also, yeah, it's actually a lesson. If you work with integrable system, you really need to take into account other charges if you're interested in questions like matrix elements. And integrable systems are huge responsibility. It's a lot of charges, but it's really required to take it into account. And then second, what I told you, that the model, the quantum Benjamin Nono system, which is integrable hierarchy of CFT, can be a nice minimal model actually to study structure of matrix elements in the thermodynamic limit. You can do some analytics, you can do some numerics, and pretty efficiently, and to see what is happening. And well, the kind of just one sentence summary, the fluctuation scale is actually important, and it's influenced the structure of matrix elements in the thermodynamic limit. So there is no any typicality. It's not that microcanonical ensemble is equivalent to canonical. If they have different fluctuation scales in this ensemble, of diagonal matrix elements will look differently, and this can be actually important, even though I didn't tell you how it can be important. But okay, so open kind of questions maybe. So analytics here, we don't do a lot of actual analytics. We do analytics with simple states, but it can be very good to perform some analytics on even with Reshik ensemble. So how to perform? Matrix elements is just can be calculated using arms and legs. So you need to know something about that. You need to know the distribution of arms and legs in your ensemble, and knowing that, the question, is it possible to then say something analytically about matrix elements? How they look like? First question, important one, I think. Another question, what about correlation functions? Finally, we are not interested in matrix elements. It's something unphysical. We're interested in correlation functions. This is something we are looking for. And is it possible to use these structures of matrix elements that I was discussing today to study correlation functions, to tell something about correlation functions? How the things that I was telling you about, the structure of correlation function, is it encoded in this somehow or not? For us, this is a bit an open question. And very important, of course. Third question is, of course, we actually study integrable system, and maybe there is indeed some particular features of this integrability, and maybe in chaotic systems, the results would be different. It's actually important to verify. I don't know how to do that, because of course, on the 20 spins, it will be very hard to do that, and there is no any exactly solvable system in terms of that, of course. But this is important thing to think about. And lastly, I was talking about suppression of matrix elements a lot, but actually it's also about the locality. But I didn't talk about locality. Why? Because I had a particular expression for matrix element. It is very important to understand how locality actually restricts the suppression of matrix elements. For me, it would be nice, important problem, like from first principles, to assume, if locality of my interaction in the Hamiltonian is like that, what can I say about the suppression of matrix elements? This, I think, also can be like important direction. That's it, I think. I think that's it. My final slide, my favorite one. Thank you for your attention. Okay, thanks.
Thanks a lot for the beautiful talk.
Thank you.
Any questions? Okay.
Мгм.
So let me make some comment concerning your nice observation. Actually, next seminar will be devoted to the paper, which is to some extent related to the similar question. And it turns out that if you consider some finite dimensional system related with a non-homogeneous XXX spin chain, or this is just Russian doll model. And in that case, it's integrable system. And in that case, there are, and let us consider two chemical potential for the Hamiltonian as well as for the for the next charge, and it turns out that quite similar picture emerges, and it's possible to look at the appearance of chaoticity and multifractality as a function of gamma. Exactly similar. The variable gamma has the same meaning in both cases, and at different gamma you have localization or multifractality or chaoticity, and all this stuff can be described in terms of properties of Bertrand-Zatz. So to some extent it's another system, but there are different questions. We posed different questions. It's our paper with Ilya Lyubimov, and we posed different questions, not thermalization, just we looked at when the system start with integrable system and look how the chaoticity could appear in that model. It's not directly related with thermalization, but ideologically it's close to some extent. And the picture is very close. So indeed, using the Bertrand-Zatz equation, it's possible to recognize the fluctuation of the next charge is responsible for the appearance of chaoticity, and moreover, there is no big difference if you consider the similar system with chaotic coefficients. So it's related to one of the question you asked at the end of your talk. It seems that in this respect, there are some similarity. There are some differences, but the picture in general is similar. So.
And this is the next Friday seminar.
It is surprising, yeah, that two talks at our seminar ideologically are related. Yeah.
Oh, great! I will come. Thanks for the time. Yes.
Surprise, actually. By the way, have you considered the fractal dimension? So since in your case you could analyze the behavior of the system by the fractal dimension, and fractal dimension changes as a function of gamma in your case.
Yeah, but fractal dimensions of what?
Wave functions. So when we consider integrable system, you can consider eigenvalues of Hamiltonian, and
yes,
just investigate the behavior of eigenfunctions function of the scale of the system of L.
Yeah. So in this case, of course, no. This there will be nothing about the multifactorial. Eigenfunctions all the time is just given by Jack polynomials.
Yeah, exactly.
And so the gamma actually does not influence the structure of eigenfunctions. They're just always given by these Jack polynomials. So as far as I take just one particular microstate, there is no any notion of gamma. He doesn't actually know about gamma. But if I take an ensemble of microstates, now there is a notion of gamma. So this, I think, in this case, it's not a defined thing. But
okay, and also there is some similarity with our paper with Polkovnikov and Rustem, and there are some other guys. And We just consider the matrix Hamiltonian. And when we consider matrix Hamiltonian,
Yeah. So I see. I turned on. So indeed, so it's like, it's like it reminds me this stuff that we are doing here. This Roserbeck-Porter ensemble, where basically people study that and then like localization, multifactoriality, blah blah. So all this stuff. Because basically what they do, they consider diagonal matrix and some off-diagonal matrix elements that scale in a way somehow with gamma, like what we can do here. So in some sense, what we are showing here, on different scales, our system looks like different Roserbeck-Porter ensemble in some sense. So there is like this off-diagonal matrix elements like have different order. But it's yeah, for now I don't see how localization multifactoriality can be important here. But maybe, I don't know. Yeah, maybe. No.
Okay, thanks.
Thanks. Okay, then. Thank you for the opportunity.
Thanks a lot.
Yes. And bye-bye.
Thank you.
Ah.